Okay, so good morning to everyone present here. So, as the name suggests, we're going to be looking at the tree ensemble layer, which again might give you a slight idea that it might be related to decision trees. Well, if you thought so, that is perfectly right. And we're talking about differentiability and conditional computation as well. So, I'll just head over to the next slide. So the abstract covers the first 4 points that I've listed out. So neural networks and decision trees. I am pretty sure most of us from sixth semester have worked with neural networks in our projects. And in the due course of the seventh semester, we've been working on decision trees in our labs and maybe in our projects for this year, final year. But has anyone ever thought, what if we combine both of them? And maybe you're thinking, why do we need to combine both of them? And that's one question we will be addressing, or the paper would be addressing, as to why they have combined both. And the third question would be, what is an ensemble of differential decision trees, or also called as soft trees? And what are the problems with such trees? So the main question, the big thing that we're going to be discussing here is, what if we merge a neural network with a differentiable decision tree? So first topic that we're going to start off with is what a decision tree ensemble is. So we know what a normal decision tree is, right? We know how a decision tree works, how it traverses each node based on how much, based on the conditions it checks. Like let's say I am trying to predict some uh, portability of water, that is our ML lab data set, for example. So we have either a 0 or a 1. And when we do a decision tree classification on it, we are checking certain conditions like is the chlorine amount less than a certain value? If yes, go to another node, for example, like that. And other than that, I don't know if anyone has noticed, but it is actually very simple. And through a lot of papers, it has been proved that you can tune decision trees more easily. You can make them robust to outliers because a lot of models usually do not handle outliers that well. But decision tree, because of its approach to be able to traverse every node, is able to cover for outliers. Then, of course, because we're talking about an ensemble here, which is basically a combination of multiple decision trees, we are bringing into consideration something called as conditional computation. So what that exactly means, again, conditional you might be reminded of probability where we did Bayes theorem, right? So that's almost similar here, except for the fact that what it means in technical terms is that it is an ability of the tree to be able to route a data sample through all possible nodes, not just a specific route. And the cool thing about this is that if, like, let's say the data sample is given as an input, it will only go through a small amount of nodes, not the entire huge structure of a decision tree. So what we deal with is a small amount of data, but there could be a larger amount of data as well. And for that, the decision tree structure might be huge. So there's a lot of computation involved. But in this case, because there is already some conditions set with some probability, you will be only accessing some small amounts of nodes. So that reduces on your computation time and you're able to put out an output faster. So now that I've talked about using a small amount or small number of nodes, I don't know how many of you remember, but from neural networks, there was a term that we use for making use of just a small number of nodes and discarding the rest. Does anyone remember what the term was?
Is it dropout?
Yeah, that's exactly what it is. So indirectly in this, you are implementing dropout. How that works is because you activated only a certain amount of nodes in your decision tree, you're not using the rest. So in a way, it's indirectly dropout, and you're also implementing regularization. However, the one thing that decision trees don't have is the fact that you need to feature engineer your attributes. And that's the only drawback or the caveat with such an ensembles. But otherwise, this is one of the best models that can be used for most applicative ML problems. So coming to the key components of this model that have been discussed in the paper. So one is the tree ensemble layer. The second is a differentiable decision tree, and the third are the activation functions that they've used. So I will start off with the tree ensemble layer. So again, we have discussed what an ensemble is. You have multiple trees. You have multiple trees working on the data that has been inputted, and the output can be very dependent on the kind of model or problem you have. So in their case, they were used about 28 data sets, including the CFAR, CIFAR, and the MNIST data set. So that is very dependent on the problem you go ahead with. Okay, Priya, one second. Yeah, so because one second. Yeah, so regularization is again a method of, as we discussed with respect to this paper, there's something called dropout. So what dropout essentially does is that you're gonna make use of only a certain amount of nodes which will function and provide you the output. Why that is useful is because in some cases the neural network might overfit the data. So what happens is you need to prevent that overfitting from happening. So you either use dropout methods or regularization. So again, as you mentioned, Priya, that there's two methods, L1 and L2. So the very basic layman difference between L1 and L2 is that in L1 you are finding the median of all the data that has been given to you, while in L2 you're trying to estimate the mean of the data. So what happens is this median or the mean data in any of the regularization is distributed over the whole data. So the data is again in some range. Let's say, for example, in case of standard deviation or something, it will be between certain ranges, right? So that prevents the models from overfitting on the data and maybe overriding the predictions and giving you wrong predictions. So that's again a very different thing that these guys haven't really talked about, but again, it's a good recap. So coming back to the tree ensemble layer, it's again how they've implemented it is a hidden layer between the neural network structure. So for example, let us assume that the layer is named as T, and there are m number of trees in the ensemble. So for any input sample X that belongs to the data, so your final prediction that's at the output layer would be the, all the M trees and how X was passed through them. So you would basically have T of X, which is the final prediction, going from T1 of X, which is the first tree, all the way to M trees. So now that we're talking about a hidden layer, so mostly when we talk about classification problems in neural networks, we make use of a softmax layer, which will find the class with the highest probability. So that's exactly what they've done here as well. So coming to this differentiable decision tree. So why is this sounding so different from a decision tree? So has anyone ever thought about how a decision tree works? Like, we learned stuff like greedy algorithms, divide and conquer, um dynamic programming. So, keeping all of that in mind, think about how a decision tree works. Like, not in the structure wise. Like, you look at the structure, you'll be like, okay, maybe we're splitting it into smaller problems, and it might be dynamic programming. But if you have you ever thought about how it's executed? Anyone? Okay, I'll just carry forward with it. So basically, how it works is you have a normal decision tree with certain conditions per nodes. So in every case, what happens is once it finds a path where all the decisions, like all the conditions are met, it will keep going down in that path. So essentially, how a decision tree works normally is like a greedy algorithm. It keeps finding where it maximizes the output, but that does not mean that it's a very accurate algorithm, right? Like there's a high possibility that you might be this whole process of greedy algorithm in a decision tree is called hard routing. So why that's a problem is because it prevents optimization, because you will only choose those nodes which are maximizing your output, no matter how long the process takes. So you have a loss function in your neural. So remember this: we're trying to merge a decision tree with neural networks. A neural network deals with loss function, which you have to minimize. But in this case, because you're not caring about how much time it takes, you are actually not impacting the loss function and basically adding on to your computation time. So that's where a hard routing problem comes. So a normal differentiable decision tree deals with soft routing. So how many of you remember in 12th grade we had a chapter in math called continuity and differentiability? Anyone?
Um, well, if it is not continuous, it won't be differential.
Exactly. So using that as the base over here, we introduce a term called soft routing. So soft routing essentially allows trees or their nodes to be able to route samples on both sides of a condition. So how that's helpful is because you're making, so think of it as a graph, right? So it's continuous between a certain range of basically it is continuous between both the nodes of the decision tree, not exactly one path. So because it has access to all nodes, you are able to construct a differentiable graph of travel or a continuous graph. So because it's continuous, if there's a high possibility it can be differentiable. And the good thing is, because it might have a possibility of being differentiable, you have a chance of implementing gradient descent based optimizing techniques because they deal with first order and first order derivatives. So you can combine this exactly with the neural network also and implement this with your decision tree and optimize it. So I'll just digress from here and show you a Jamboard that I just came up with. So essentially what I mean to explain is, let's say I have a node L over here, and as I mentioned before, in soft routing, you have a chance, all the nodes have a possibility of visiting. So this might have, say, some probability P1 and some probability P2. You're not completely overriding this or like not accepting it. So let's assume that I have to reach a node, say L. So the probability of X reaching L, or like, a condition reaching L would be, so because we're talking about neural networks, the most common, the most fundamental unit of a neural network is its weight. So for every X neuron or a node over here, we will have an associated weight. And let's assume that the probability of going left is L, left arrow I, and the probability of going right is again the arrow the other way. So because we have a probability associated with the right side as well, and we only want to concentrate on the nodes going to the left because our L is over here. So we will, again, the usual probability multiplication, we will have the associated probability for the left, but we need to also exclude this. So we'll be doing 1 minus P times the right probability. So we get the probability of going down here better. So that's, again, a very layman explanation because it's a very simple decision tree structure. I'll just go back to presentation. Yeah. So soft routing, again, as I mentioned, basically gives you a probability of each node being visited. So that ensures that every node has a possible probability of has a positive probability, which means that you can reach it at some point of time. So the last topic last major topic that I feel we should cover in this would be the activation functions. So how many activation functions do you all remember, like on a very general basis?
Can you like go through the soft routing and hard routing once again? Like it was a little difficult to go through.
Okay, so I'll just repeat the same again. So basically, in a greedy based algorithm is how decision trees work. You will pursue only a particular path, which is based on the conditions that how decision tree works. So you have a particular path as to how I should reach that particular node, right? But that is in consideration to the fact that you're not going to be caring about how long it takes for me to reach that path or that particular node destination. So that's hard routing, okay? And that prevents optimization from happening because at the end, what the decision tree decides to do is to maximize its output, regardless of how long the path is or how short the path is. So you will also have discontinuities with respect to the loss function because you're trying to incorporate a decision tree with a neural network. So it's very hard for them to be able to merge together and work at a common problem. Whereas in soft routing, you're assigning each node a probability, and basically on say like one node would have two branches, right? So each node that can be visited would have a certain probability. So you are basically making it easier for the decision tree to decide which node to take, and in this case, you're making it easier for gradient based optimization functions to take care of, to be there because it's a neural. You're trying to again incorporate this with a neural network, right? So that's basically soft routing.
So essentially, hard routing is same as soft routing, except probability will be 0 or 1.
Yeah,
like
exactly.
There's no range. Okay.
Yeah. Cool. I'll just move on to the activation functions then. So yeah, as one second. Yeah, as Priya mentioned, the sigmoid tanh ReLU that we have most commonly come across, sigmoid as well. So what the problem over here that they have mentioned is, why is sigmoid a bad choice for this model? So one thing is what we need to understand is sigmoid generates a positive probability for all paths. But that does not mean that, let's say there is a node which is to be discarded. Like it shouldn't be considered at all. Sigmoid will still provide some probability of that path to be happening. But the thing is, we don't want that happening, right? The whole point of this optimization is to discard certain nodes to prevent overfitting and to reduce computation time, right? So sigmoid is generally not a good function for this. So what they have proposed is not tanh, not ReLU or any other thing. They have decided to go ahead with a parametric equation in the form of a third polynomial degree. So what that basically means is they have defined a function S. Yeah, so I'll just write it out. So sigmoid basically, as I mentioned, they were it generates a positive probability for all paths. But like as I mentioned in the first few initial slides, we want to discard a few nodes because we need to implement, because it indirectly implements regularization, and you don't have to pursue those paths because we are concerned about the computation time over here. So what they have suggested, or what they have decided to implement as per their research and on the basis of 26 other data sets that they've experimented with, they have come with a function S of t, which is a third degree polynomial function with a parameter t. So what t exactly is, I will explain. So this is exactly the equation that they have used, and they have come up with a parameter lambda, which is very dependent on the critical. Basically, lambda deals with the critical points that they have come across with a lot of math involved, which I wasn't really sure of either. So they have come across with a range of minus lambda comma 2 by 2 and lambda by 2. So there was some, I will share the link of the paper as well because it took me time understanding it too. But in and out, they've come across a parameter t, which belongs to a range minus lambda by 2, comma lambda by 2. And you remember how we had in linear algebra, we had to maximize a certain function or minimize a function. So we definitely had certain points on which the function will be minimum or maximum. So those points are called the critical points. And as per their research, they've come across the critical points to be as a condition where at minus lambda by 2, the function would yield a 0. At lambda by 2, the function would yield a value of 1. So essentially, this function, the maximum ranges would be between, because the range of t is between this. So essentially, these are the conditions that they have put forward, and because they're also dealing with gradient-based optimization methods, they've also come up with the first-order derivative conditions, which is the first-order derivative at minus lambda by 2 and is the same. The value should be the same at lambda by 2. Okay, just slow down a bit. So I'll start again. So this is the function that they have planned on incorporating for their optimization. So
I think you can explain once and then go. Let them read the paper and maybe get more clarity. I
yes, ma'am.
understand that going into depth of mathematics, you also may not be so comfortable. It's okay, whatever you understand. Once you can repeat, but others can just go through the paper what he is going to share, because
Yes, ma'am.
he has just read one paper and trying to present. So you don't have to like in depth go how much ever you are comfortable, you can present. That's enough.
Yes, ma'am.
Okay, you
Ma'am,
can maybe
actually
once
very well said.
repeat. Yeah,
Yes, ma'am. So
yeah.
again, I'll just repeat this whole thing once. So they have come up with a equation in the form of a third degree polynomial where they have decided that t, that is their parametric variable over here, belongs in a certain range of minus lambda by 2 and lambda by 2. Now, again, how they arrived at lambda, they've given a very huge explanation, which is a lot of math. So I thought I'll let everyone else do the reading because it, of course, is a huge explanation there. So how they've defined the critical points over here is minus lambda by 2 and lambda by 2, as we know from the t's range. And they have specified that minus lambda by 2 should, the function's value would be 0 at this range, and at the maximum range it would be 1. Now how this is useful as compared to a sigmoid function is because sigmoid does not exactly output zeros or ones. It gives a probability of some value to each node. But we also need to discard some nodes, right? So they need to have a probability of 0. So this function is what they help them in being able to discard nodes with some probability 0. So again, there's another. How many of you remember normalization in neural networks? Like, batch normalization. Anyone remembers? Okay. So how batch normalization works is, again, for every group of data that you have, for every neuron you would be normalizing the data, and how that helps is basically it prevents the internal nodes from having a zero gradient. So that's a gradient problem again. So now that we've decided that these people have come up with their own activation function, which again deals with first order derivatives, you can use optimizing. So now that they were able to do this, they were able to merge neural networks and a decision tree together, differentiable decision trees, and so now the whole sole role of this activation function is to optimize the tree ensemble layer that we talked about before. So the only main bottleneck that had to be dealt with over here was the fact that there would be a lot of gradient computation, because if you have a huge decision tree structure, you will have a lot of gradients to compute for every node that you have. And of course, this is a memory complex operation as well. So that's another problem that they had. However, one thing to note is that because you're dealing with first order derivatives over here, you can also make use of optimizing functions such as the stochastic gradient descent and other such optimizations. Other than that, I think after this they've explained how it worked and performed on each of their data sets. So I will I will drop the paper link below. So I think all of you can have a look at it, because explaining the math part, I think it'll be easier if everyone reads it at their own pace. So yeah, that should be it. Yes, ma'am, I'm done.
Okay, Ritvik. Good job. See, why I said he need not explain is already people were very hesitant to come up. So at least somebody has come up. So whatever